Hello, welcome to lecture 20 of the course. In the last lecture, we have seen the consequence of considering light as a stream of photons, and we discussed the so-called photon statistics. We'll continue our discussion on photon statistics in this lecture as well. However, apart from that, we are going to discuss an important concept called correlation function, in particular the second order correlation function, which is of immense importance for experimental quantum optics. Also, we are going to discuss coherent states of light. So let's begin. In the last class, we have studied the consequence of quantization of light. When we consider light as a stream of photons, we find that even if the average photon flux can have a well-defined value, the photon number on a short time scales fluctuates due to the discrete nature of the photons. And in this context, we studied the photon statistics and we found that the perfectly coherent light exhibits the so-called Poissonian statistics, and the most prominent characteristics of Poissonian statistics is that the variance is equal to the mean photon number, or the standard deviation is equal to the square root of mean photon number. Apart from that, we have also seen that depending on the nature of the photons or the light, there are other three kinds of statistics this stream of photons can show. One is the so-called sub-Poissonian statistics, where the standard deviation of the photon fluctuation of the photon number is less than that of the square root of mean photon number. And then super Poissonian statistics, where the standard deviation is greater than that of the square root of the mean photon number, and this is shown in this typical plot where with the photon number is mean photon number is taken to be 100, and as you can see that the super Poissonian case, the photon number distribution, the probability distribution is broader than that of the Poissonian one, and the sub Poissonian has a the broadening is narrow in terms of the probability. The distribution is narrower compared to the Poissonian one. And also, already as I said, that the perfect stable light have a constant intensity and it exhibits Poissonian statistics, and all classical light with time varying intensity shows super Poissonian statistics. For example, the so-called thermal light, and we have studied the statistics for the thermal light as well, and what we have found that the thermal light exhibits the so-called Bose-Einstein statistics, not Poissonian statistics. However, this analysis, we should emphasize that the thermal light, only a single mode of the radiation of the thermal light shows Bose-Einstein distribution statistics. This is important to remember, and the mean photon number in a thermal light is given by this expression. And as you can see, the nature of the probability distribution for the thermal light and the stable laser light, which shows Poissonian distribution, is different here, as it is evident from this particular plot. And as it is clear from these two expressions that this variance for the thermal light is greater than that of the coherent light, and this expression, this just I have written it, but I am going to show it explicitly in the problem solving session. Now let us discuss about, because having now got some idea about the photon statistics, let us now discuss about how an external light field that we want to detect interacts with the detector. You know that in a laboratory, fields are directly measured by photo detectors. You can see a schematic of a photo detector in this plot here. These are actually devices in which an external field interacts with a photocathode composed of atoms ionizing them, and this process results in the emission of photoelectrons that form a photocurrent whose intensity or fluctuation are then measured. In this schematic here, we can see that the incident light ejects single electrons from the photocathode, which then triggers the release of a large number of electrons in the multiplier region. Okay, this results in the generation of an output pulse that is large enough to be detected by electronics. Please note that this method is used to detect very weak beam of light. In order to detect high intensity light beam, photodiodes are used. So here is a diagram for photodiode. Now here you can see in the schematic that a high intensity beam is incident on a photodiode detector. The time dependence of the photocurrent fluctuation relates to the photon statistics of the incoming beam. Now in this figure B here, it shows the simplified diagram for the detector circuit. The diode is reverse biased, as you can see from the diagram, with voltage V0. The photocurrent I of t generated in the detector flows through the load resistance RL, okay, and AC voltage across the load is then amplified to produce a time dependent output voltage V of t. The capacitor C here blocks the DC voltage across this load resistance RL from the amplifier A. Now measurement of the DC voltage across RL, this load resistance, permits the average photocurrent I to be measured. I hope you got some idea about the detection process. Now let me discuss about the semi-classical theory of photo detection. Semi-classical because here I am going to consider light as a classical entity. Now you see in the semi-classical theory of photo detection, the probability to detect a classical field of light of intensity I of RT, this is the intensity. Now here in this inside this bracket I am putting, that means it is the average intensity. I of RT is the intensity of light. In semi-classical theory of photo detection, the probability to detect a classical field of intensity falling upon a photo detector kept at a distance say r, okay, in the time interval t to t plus delta t is defined by this equation. And here in this equation, eta is the efficiency of the detector, and I of RT in this bracket, okay, close bracket, is the average intensity of light evaluated at the location R of the photo detector. The average is taken over all possible instantaneous value of intensity I of RT, and that's why it is the ensemble average. Now in terms of the field amplitudes, this average intensity can be written as E star of RT, E of RT. Then the photo detection probability can be rewritten in this particular form, and as you can see, eta here, as I have already told, is the efficiency of the detector. Now if we defined a function which is known as the first order correlation function g1 of RT as the average of the multiplication of the electric field conjugate E star R of t E of RT, then in terms of the second order correlation function, I can write down the photo detection probability of the detector at the location R, where the detector is actually positioned. We can express it in this particular form, and it's very useful formula. And as you can see, and in fact it is evident from this formula that an experimental measurement of the average intensity immediately provides the information about the first order correlation function of the detected field. Let me now discuss about the so-called second order correlation function, which is quite important and useful for us. Let's say we have two detectors, one detector located at a distance R1, say detector number 1 D1, and another detector is located at a distance R2, detector number 2 D2. Now the probability for detector at the location R1 to register a photo detection at time t1 within the time interval delta t1 is given by this expression, and here eta 1 is the efficiency of the detector 1, that is D1. And then similarly, the probability for the detector at the location R2, that is D2, to register a photo detection at time T2 within the time interval delta 2 is given by this expression. And eta 2 here is the efficiency of the second detector. Now we can define the joint probability for the two events. That means the detector D1 and detector D2 detecting their respective photo detection. This joint probability can be given by this expression. And as you can see here I am taking the average over the product of the intensity that is measured at the detector located at R1 and the intensity measured at the detector located at R2. So this is the product. I am taking the average over the product of the intensities, respective intensities measured at the detector D1 and D2. Eta 1 and eta 2 are the efficiency of the detector D1 and D2 respectively. Now, if we define a, by the way, before I go to the second order correlation function, you see that if this average of the product of the intensities is equal to the product of the average of the individual intensities, average intensities, if I can write it in this way, then the detection processes are independent of each other. And if we cannot write it this way, then that means that the detection processes are correlated to each other. Let me repeat once again that if I can write the average of the product of the respective intensities at the detector at R1 and R2 as a product of the average intensities that is measured by detector at R1, that is D1, and the another detector located at R2, that is D2, if I can write it as their individual average, product of their individual average intensities, then that means the detection processes are independent of each other. And if we cannot write it that way, that means they are not equal. I cannot write it as a product of their average intensities, individual intensities, then the detection processes are not independent of each other. That means they are correlated to each other. And this is a very important point. Now, if we define a function the similar way that we have done it for the first order correlation function, now we are writing it in terms of the electric fields. Now, this is called the second order correlation function, and as you can see here that this, while I am defining this second order correlation function, the way it is written, the fields are written is called normal ordering. So please notice the way the fields are written here. You see E star R1 T1, then we are writing E star R2 T2, then after that we are writing E R2 T2 and then E R1 T1. Okay, so this is called normal ordering. Then using this definition we can write down the joint probability of detection at the two detectors. In this simple formula we can use this. So here again eta 1 and eta 2 are the efficiency of the two detectors and Z2 is the second order correlation function. Now the probability of a single photo detection is proportional to the product of the intensity and the efficiency of the detector. So therefore the average number of photo counts can be written by this expression, and in fact it can be shown that the probability of detecting n number of photons is given by this expression, and it can be worked out very easily. Let me actually give you a proof of this. To do that, let's say, to do this, let me do it in the reverse way. I have my average number of photo counts is equal to n number of photo counts into the probability of detecting the photo counts and photo counts. Now here let me put the expression for the probability, that is what I have written. So if I put it here, let me take this average sign here. I have here n eta I to the power, I'm just writing this expression here, this probability of detecting this, replacing the whole expression here. I have this divided by n factorial e to the power minus eta I average. Okay, so let me write it this way. If I write eta I, and then you can write it as d of d eta I, then I have summation over n factorial eta I to the power n e to the power minus eta I. And I urge you to just verify it, that you are basically going to get this expression if I write it in this way. This expression is nothing but e to the power eta I, and therefore I can now write it as eta I e to the power eta I e to the power minus eta I, and hence I have eta into the average, right? Average of intensity. Okay, now what about the variance of the number of photo counts? Well, it can be also calculated very easily. To do that, however, you can first show that n square, average of n square, is equal to eta into average of intensity plus eta square I square. I request you to try to get this expression, and you can easily work it out. And if you cannot, then please refer to my problem solving session number 6, where you will get the hint. And if you utilize this result here, average of n square, then the variance of the number of photo counts can be easily calculated, because the variance of the number of photo counts, that is delta n square, is equal to average of n square minus average of n square, right? So this you all know. So now if I put the expressions for average of n square is eta I average I plus eta square I square, okay, and then I have here average of n. I have already worked out here, average of n, that is mean photo count, and therefore square is going to give me eta square average I square, and which I can now write as eta average of I plus eta square. If I take it common, then I have here I square minus I whole square, right? And this guy is nothing but the variance in the intensity. This is delta I square. So therefore I can write variance in the photo counts is equal to eta I is, by the way, nothing but the average of photo count, that is n, plus now I have eta square into the variance in the intensity. So this is the expression I get for the variance of the number of photo counts. Now this relation has a simple physical interpretation. As you can see, the fluctuation of the photo counts are proportional to the fluctuation of the intensity of the incident field. Now if there is a non-fluctuating field, such as the stable laser case, for non-fluctuating field, which represents a coherent field that we discussed earlier, for a non-fluctuating field, your variance in the intensity is going to be equal to 0, and in that case we will get this variance in the photo counts is equal to average of the photo count, or which we also write it as n bar, and this result is already familiar to you, and you can see that in a non-fluctuating field generally, it obeys the so-called Poissonian statistics. On the other hand, for say fluctuating field such as a thermal light, say thermal light, we have already discussed about the statistics of thermal light. In that case, you have this variance in the photo count is greater than the mean photo count, right? This already, it is also quite evident from this particular expression here. And so this actually we already know. Now in this expression here, this first term, this variance of photo counts in this expression, the first term on the right hand side represents the so-called short noise. What it means is that, you see, this is associated with this short noise, I mean to say, is associated with the random generation of discrete photoelectron counts in the detector. On the other hand, the second term refers to the so-called wave noise, and this is basically the noise in excess of the standard short noise, and it is often named as wave noise. Now we are going to discuss the so-called quantum theory of photodetection briefly. From quantum mechanics, we know that the probability of finding a system located at some distance r and described at time t in a particular state, say ket n, is given by this expression where this psi of rt, ket psi of rt, represents the quantum state of the system, and ket psi of rt is the arbitrary state of the system, and ket n is one of the eigenstate of the system. So this is already well known to you from your elementary quantum mechanics course, and already this also I have discussed in my initial lectures. Now this state ket psi of rt obeys the so-called Schrodinger equation. As you know, this obeys this Schrodinger equation, and you know that this Schrodinger equation has this perturbative solution. If I keep only the first two terms, then the perturbative solution is of this type, and here H is the interaction Hamiltonian. Now this interaction Hamiltonian, you know that it can be written in this form: H is equal to minus mu dot E. Mu is the dipole moment operator, and electric field also we are taking it writing the operator form now. The whole thing is now treated quantum mechanically. It's no longer a classical approach. Now the dipole moment of the atom is in the where I am considering the atom is actually in the photodiode or in the photocathode. Now, as we discussed in lecture 4 earlier, that we can write under the so-called RWA or the rotating wave approximation. If you recall that we can always decompose this mu as having two parts, mu plus and mu minus, as we have done in our lecture number 4, and that electric field also can be written in this form. It has two parts, E plus and E minus. E plus and E minus basically refers to the positive frequency and the negative frequency part of the electric field respectively here. Now therefore you see, we can therefore write, if I take the scalar product of psi of t with ket n, then this is the expression we get on the right hand side. I just have multiplied this equation, have taken the scalar product of this equation with ket n, and this is what we are going to get. Now if the detection time is very short and we are interested only in the upward transition, that is the absorption of the external field, then we can write this to be, because this transition has to happen via the interaction Hamiltonian. So therefore this term is not going to contribute at all. We can consider it to be negligible, and then this part is going to contribute because we are interested only, as I said, in the upward transition, that is the absorption of the external field. So this gives us the probability of transition, and that is going to have this particular form. This is the probability of transition, and from here I get this particular expression for the probability. Now here A is a constant, and which includes the dipole moment of the atom. Also, while I am taking A as a constant which includes the dipole moment of the atom, here it is assumed that the dipole moment remain constant during the detection time. Okay, that's the reason I am including the dipole moment inside this constant A. By the way, we cannot predict the final state of the atom, as the electron in the detector can be in any state. Therefore, we need to sum the probabilities over all the possible states. So therefore, summing over all possible states, we can get the expression for the probability of transition in this form. Here I have just taken the summation over all the possible states. This actually, let me open it up, and if I open it up, then I have a square t square by h bar square. H bar is the Planck's constant, and this, it has a complex conjugate, it's a modulus square. So therefore I can open it up, and then I have here, this would be psi of 0, and this would become now E minus RT. Okay, and then I have here N K10, and then I have this N E plus R of t psi of 0. Okay, just I have opened this particular term, then this is what I get. Now let me further do the simplification. A square t square by h bar square psi of 0. I have here E minus R of t. Let me take the sum over n here, and here I have K10 bra n, and then I have here E plus R of t psi of 0, and as you can see, because of the completeness condition, this is identity, and therefore I can write it as a square t square by h bar square psi of 0 E minus R of t E plus R of t psi of 0. Okay, this is what we get. Now if we define a function, the so-called quantum first order correlation or coherence function, now using this second order correlation function, I can therefore write down the probability of transition P of R t is equal to, I will have simply a square t square by h bar square z1 r of t. 1 is basically refers to the fact that it's a first order correlation function or coherence function. Now proceeding in the similar way, we can find the joint probability that a system described by the state k psi of rt will be found in the state km at time t2, which is greater than t1, at a certain location r2 if it was found in the state kn at time t1 at the location r1. So here you see, now I am trying to find out the joint probability of transition involving detection at two locations r1 and r2. Let me again explain this particular term here. It is analogous to what we have done in the classical context. Here it refers to the joint probability that a system described by these state vectors k psi of rt will be found in the state ket m, which is one of the eigenstate of this arbitrary state, at time t2 greater than t1. That means you are observing the system at state ket m at time t2 later on, and earlier you have observed the system in the eigenstate ket n at time t1 at the location r1. I hope you get the idea here what this term basically means. Then in the similar way, you can actually work out the expression for this probability of joint probability of transition. So this is what you are going to get it. If you look at it carefully, you will find that it is not difficult to understand. Here, as you can see, we are defining this second order correlation function, and this second order correlation function is defined in this particular form. And here also please note that these operators, electric field operators, are written in a particular way, in a particular order, and it's basically done in the both time ordering as well as the normal ordering of the field operator is utilized here. So I will not explain it much, but you just please keep this particular form in mind, and this is going to be pretty useful for us later on. And therefore this quantum second order correlation function, which is of immense importance, and it has a very important meaning, and it's actually not difficult to understand its physical meaning. It basically refers to the fact that it is a relative measure of the joint probability that a photon is detected at a point r2 in time t2 if one was detected at point r1 in time t1. Let me say it again. Z2, which is the second order quantum second order correlation function, it basically gives the probability, joint probability, that a photon is detected at the point r2 in time t2 if another photon was detected at point r1 in time t1. Okay, so this is very important, and we are going to utilize this concept soon. Now, this second order correlation function can be measured experimentally in a laboratory, and this is a typical schematic diagram to do that in laboratory. Let me explain what it basically is doing. You see in this schematic here, it shows the experimental scheme for the measurement of the second order correlation function. Here an incident beam, this is the signal beam that is incident on a beam splitter, a 50-50 beam splitter, and it is getting divided into two beams having intensity I1 and I2. I1 is detected by the detector 1 and I2 is detected by the detector 2, and the signals from the detectors are then multiplied. You see they are now getting this signal, and this signal is getting multiplied here and averaged over all detected values, and it gives the second order correlation function I1 I2. By the way, as you can see from this expression here for the second order correlation function, these electric field, as you know, are associated with the intensities, and E minus and E plus, for example, they are complex conjugate to each other, right? That's why that is going to give you the mod of E square, which is again related to the intensity. That's why the second order correlation function, as you can see, is basically the product of the intensity operators for the two detections, for the two intensities I1 and I2. So if you can measure the intensities, product of the intensities, then you are going to be able to find the second order correlation function. So that is basically the idea here in this experimental setup also. I hope you are getting it. We will now discuss the second order correlation function for various quantum states of light. First of all, let us discuss about the photon number states, and we know that photon number state refers to a state of light
which is represented by a say ket n, and this particular state refers to the fact that there are n number of photons, are there in the field. Okay, so this we know, and actually photon number states is also known as the so-called Fock state, or number state as well, Fock state or the number state, because we are considering this particular Fock state in the context of electromagnetic radiation or light, so that's why it is also termed as photon number states. Earlier we discussed about the quantization of light, and the electric field operator for an electromagnetic wave, that is a standing wave or standing wave light, is written in this form. The electric field operator is say I eta. This is the polarization direction. Then you have this normalization constant h cross omega epsilon 0 v. V is the quantization volume, and you write it in terms of the annihilation operator and the creation operator, and because it is a standing wave, so you have this term sine kz, and this standing wave is propagating along the z direction. In fact, as you can see, this form of the electric field operator clearly shows one fact, that electric field operator is a Hermitian operator. In fact, we can write this electric field operator in this particular form as well. There's another form which you may encounter in some other textbook, in some textbooks. So you have, say, it would be s cross omega by epsilon 0 v square root. Then instead of putting I here, you just write here it as a of t plus a dagger of t sine kz. Now if you look at it carefully, you will again see that this operator is also Hermitian. And by the way, a of t, as you know, it has a solution of this type. It would be a of 0 e to the power minus I omega t, and that means this annihilation operator oscillates with frequency. Positive frequency part is omega, it oscillates with omega, and a dagger is a dagger 0 e to the power plus I omega t. Okay, so I think this you should know. In fact, I can write it in this particular form also, a convenient form. Eta, there's a polarization direction, e0 is this constant I'm writing here, and then I have here a of t plus a dagger of t sine kz. In fact, even better if I can do, okay, before I do, let me just write another form of this. This I can write it as two parts, e dagger plus, and then e minus, e plus and e minus. Okay, so I'm just writing it in this particular form. I'm decomposing this electric field operator to this particular form. Now here this e plus operator refers to the term eta e0 a sine kz. Now this basically represents that part of the electric field operator who is oscillate with the positive frequency, that is omega, because I think I have already explained it in lecture number 4 earlier, where you see you can write it as e to the power minus I omega t refers to the fact that you are dealing with a positive frequency omega. This is what I mean. And as I have already told you that a of t oscillates with frequency, this has the solution a of 0 e to the power minus I omega t. And on the other hand, that's the reason E plus refers to the positive frequency part, and similarly E minus refers to eta E0 A dagger sine kz, and here A dagger oscillates with this, it has this evolution part. If you have already seen here that it goes like e to the power plus I omega t, and this I said it is oscillating with the negative frequency, right? This is what I mean by negative frequency, because this minus omega I can write it in this form. So that means E minus refers to the negative frequency part of the electric field. So therefore I can now write the electric field operator in this decomposed form E plus and E minus, this actually I can write as eta E0 sine kz A of t plus A dagger of t. And now you see here that this quantity I can just write it, it's a constant parameter. If I write, I can write it as a lambda. Then I have this convenient form. This is convenient for our calculation purpose. I can write it the electric field operator as lambda A plus A dagger. Now also note that here E plus, which is again very useful for us, it will turn out to be very useful later on. E plus refers to A and annihilation operator, and E minus refers to the creation operator A dagger. Now the photon number state, as you know, for a single mode light field refers to the eigenstate kten of the number operator. Let me denote the number operator by n cap, and n cap is equal to A dagger A. Alright, and this number operator satisfy this eigenvalue equation. N cap operated on the number state or the Fock state or the photon state is going to give n. Okay, and in fact it is n cap is A dagger A ket n, and that is equal to n. So this is what I mean. This all we have, and the fact that this number state ket n is also the eigenstate of the single mode field Hamiltonian H. Therefore it satisfies the another eigenvalue equation. You have ket n satisfy this eigenvalue equation also, and here you know this Hamiltonian is nothing but the simple harmonic, it's similar to the simple harmonic oscillator Hamiltonian, A dagger A plus half, and you have En as well. En is the energy eigenstate, that is equal to n plus half h bar omega. These are already known to you from your quantum mechanics course. As I have already told you that n refers to the Fock state or the number state, which refers to that state for which n number of photons are there, and this means if I have k0, this basically means that there is 0 photons. There is this particular state refers to the fact that there is 0 photons in the field. Okay, 0 photons in the field, and this state is also sometimes, in fact many times, it is also called the vacuum field, because there are 0 photons or no photons are there in the field. It is called the vacuum photon state. Also, the number state can be generated by from your quantum mechanics course also, that it can be generated by repeated application of the creation operator on the vacuum field. And maybe you already know that if I operate on by the A dagger operator, that is the creation operator n times, and this is the expression you will get. If I operate on the vacuum state, then I will be able to create this photon number state n. Okay, this already must be familiar to you. Now, what about the correlation function for the photon number state? Before I discuss that, let us discuss a bit more on the second order correlation function. Well, we have seen that the second order correlation function is defined as Z2 R1 T1 R2 T2. This already we discussed, and this is equal to average over this normal ordered and time ordered electric field operators at various locations. In fact, 2 locations, R1 and R2. R1 T1 here, and I have E minus R2 T2, and we also have to write about the E plus as well. So we have E plus. Now you just observed how I am writing it. It's called the normal ordering and time ordering, R2 T2 and E plus R1 T1. Okay, so this is the second order correlation function. However, you know that it's more convenient to use the normalized second order correlation function rather than this form of the second order correlation function. Let me use the so-called normalized second order correlation function. And normalized second order quantum correlation function is pretty useful in many calculations, and it is normalized. Actually, it determines correlation relative to the intensity of the field, and it is defined in this way. So I'm going to use the same symbol Z2 for the normalized as well, only slightly there is going to be a change in the expression. In the denominator there will be a term because I'm normalizing with respect to the intensities. And okay, you will see it immediately now from this expression here. The here numerator would be the same, e minus r1 t1 e minus r2 t2 e plus r2 t2, be careful here, r2 t2, then I have e plus r2 t2, okay, divided by, now I'm normalizing it with respect to the individual intensities, the two locations. So I have e minus r1 t1, okay, and e plus r1 t1. This is one term, and the another one is you have e minus r2 t2 e plus r2 t2. Okay, so this is the definition of the normalized second order correlation function. Now, to make our life easy and to get the things simple, let us consider and actually let us confine ourselves to the situation, to the case where we have r1 is equal to r2 and t1 is equal to t2. Then also we are going to replace this e minus with the, you know, the annihilation operator, e minus for the creation operator and e plus for the annihilation operator. If I do that, then we can rewrite this second order normalized second order correlation function. I'm not going to mention about this it's a r and t dependencies here because I am already considered both of them at the same position at the same time. R1 is equal to r2 and t1 is equal to t2, and replacing these electric fields by their corresponding annihilation and creation operator. So here I am going to write the numerator in this form. I am going to have, you can easily make it out, you will have here a dagger a divided by a dagger a and a dagger a. I hope you can actually see it very simply because I'm just replacing here in this expression the corresponding, you know, electric field operators by their corresponding creation or annihilation operator. Then I am getting this second order correlation function for the quantum case. And also what I can further simplify it if I use this relation. You know that creation and annihilation operator satisfy this commutation relation, a dagger is equal to 1. So this you can easily make it out. From here I can write a dagger a is equal to a dagger minus 1, which I can utilize in my expression for the second order correlation function. What I am going to do, I am going to write here a dagger here, and this a dagger a I will replace as a dagger minus 1 a, okay, and then in the denominator I have a dagger a whole square, right? This is what I have. And okay, now let me write it once again. I can now write the numerator as a dagger a, and I have a dagger a minus a dagger a, and here I have a dagger a square. And instead of writing a dagger a, let me replace it by the number operator n. So here I am having 2n, so n square. Okay, this is what I am going to have. Okay, just a minute, I have to do it this way. This would be two terms, n square, and then I have here n, and in the denominator I am just going to have, here I have to write n square. Okay, so this is what I am going to have. So this is the expression for the second order correlation function in terms of this number operators. I can actually include the information of variance also in the expression, because I know the variance delta n square is equal to n square minus n whole square, right? So utilizing it, I can write down the expression for the second order correlation function. Please do it yourself, it's very trivial. You can show that it would be simply 1 plus, you will have here delta n, the variance, okay, square minus n divided by n square. So this is the expression that I am going to use for my analysis of the second order correlation function for various quantum states of light or the electromagnetic field. This formula for the second order correlation function shows that depending on the fluctuation of the number of photons, the second order correlation function z of 2 can be less than 1, or it can be equal to 1, or it can be greater than 1. So let us examine the case of photon number state. You know, in the case of the photon number state, the variance in the photon number is equal to 0, and the average of the photon number is simply equal to the number of photons in the field. And it can be very trivially shown that the variance in the photon number is equal to 0 in the photon number state, because you see that delta n square, the variance is equal to n square minus n, and just you know that this n square, if I work it out, n square is simply equal to, you apply by this number operator square on the Fock state or the photon number state n, and then you are having again multiplied by the bra of n. Now because n, when it operates on the number state n, it gives you this equation. So you can immediately see from that you are applying on the number state twice, so therefore you are going to get simply this number n square, and therefore as you can see from here, okay, this is actually n square. So as you can see from here you will get n square, and from here you will have n square. So this is going to give you 0. So variance is going to be equal to 0, and the average of the photon number is again equal to, as I said, it is the number of photons in the field. So using these two facts, we can immediately get from the expression for the photon number correlation function, second order correlation function, that Z2 is equal to simply 1 minus 1 by n for photon number state. And you see that for a single photon field where the number of photons in it is equal to 1, so therefore the second order correlation function is equal to 0. In fact, let me tell you another thing, that this variance of the photon number is equal to 0 in the case of photon number state is very easy to understand, because of the fact that by definition the photon number state means that there are n number of photons in the state. Because we know the number exactly, therefore there cannot be any fluctuation, so therefore the variance, that means the photon number fluctuation, has to be 0. Okay, now if we consider a Fock state or the photon number state which has a huge number of photons in it, say n tends to infinity, the second order correlation function is going to be equal to 1. So therefore for a photon number state, the second order correlation function is going to lie between 0 and 1 depending on the number of photons in the photon number state. Alright, now in fact let me also make one point, interesting fact about this second order correlation function if it is less than 1. You see, as I have told you earlier, that this second order correlation function is related to the probability of finding two photons. So when the second order correlation function is less than 1, it means that the probability to find two photons together at the same location is very unlikely. It means that the photons in the field are separated from each other and move individually rather than in groups. This phenomena is known as photon anti-correlation. The photons are anti-correlated in the sense that the probability of appearance of a pair of photons at a particular time is very small. Now, when the photons are separated in time, they may exhibit a phenomena called anti-bunching. That is, the correlation function must satisfy this particular inequality. Here, this tau basically refers to the fact that these two photons are separated in time by amount this tau, and in that case the probability to detect two photons separated by the time tau is more likely than the probability of detecting two photons at the same time. Now, what about the second order correlation function for the thermal light? As you know, for the case of the thermal light, the variance in the photon number is given by this expression, and using this expression in the formula for the second order correlation function, you can see that the second order correlation function is simply equal to 2 for thermal light, and it basically means that in thermal light the correlation between the photons are very large. In other words, the photons tend to group together. So that's why you see, no doubt, thermal photons obey the so-called Bose-Einstein statistics, and this effect is called photon bunching. Now, what about the Poissonian light? For the case of the Poissonian light, I mean to say about the second order correlation function, for the Poissonian light, the variance in the photon number is equal to simply the mean of the photon number, and again utilizing it in the second order correlation function formula, you see that the second order correlation function is simply equal to 1. This implies that the photons in Poissonian light, which is also called coherent light, are independent of each other. Now, let us discuss about coherent states of light in somewhat good details. First, I will take a very simple approach. You know that the coherent state can be thought of as a eigenstate of the annihilation operator. Here A is the annihilation operator. K at alpha represents the coherent state, and this alpha, this is a number, and it's a complex number because this is, though it looks like a eigenvalue equation, but here, as you know, this annihilation operator is a non-Hermitian operator, and that's the reason this number alpha is a complex number, unlike a real number, which should be the case for a Hermitian operator. So here this alpha is a complex number. Now this this coherent state K alpha can be written in terms of the photon number state very easily if I utilize this ploy here, because this is the completeness condition. I am just using the number state as my basis states here. In terms of this number state or the Fock state or the photon state, I can write K at alpha, the coherent state, as a superposition of these number states, and here this Cn, which is a complex number, is given by this expression. Now Cn mod square has this physical interpretation, the probability that n photons in the field being in the coherent state K at alpha. Now let me operate on the both sides of this equation, eigenvalue equation, by this annihilation operator. So that's what I'm doing it. Basically what I'm doing, let me again reiterate that K at alpha, I'm now able to write it as a superposition of the number states. Now both sides of this equation I'm applying the annihilation operator here, and then I'm getting this equation on the left hand side, and the right hand side I am utilizing this particular formula, which you must be aware of, that it is equal to root over n minus 1, and then I am getting this equation on the right hand side, and then from the left hand side I have K at alpha is this, okay, and from here I am getting this equation. this equation I can just, instead of writing it ket n minus 1, I can convert it to n. If I just add here n plus 1, if I do that, and this will give me alpha n cn n ket n is equal to this equation. Now if you compare both sides of this equation, then we must have alpha cn should be equal to root over n plus 1 into cn plus 1. This gives us the recurrence relation cn plus 1 is equal to alpha divided by root over n plus 1 cn. So now using this, I can get C1, I can write it in terms of C0. You can just look at it and you can simply see I can write C2, C3 and so on in terms of C0, and utilizing this I'll be able to write this coefficient Cn in terms of C0, and therefore the coherent state I can write in this particular form here. But still I have to find out what is C0. That can be easily found out if I use this fact that this coherent state has to be normalized, and maybe I will do it in the next class because this class is already getting lengthier. So using this normalization condition, please try it to get that C0 can be shown to be having this value, and using the value of C0 I can write the expression for the coherent states of light in this particular form, and this simply means that I can write coherent state as a superposition of the number states or the Fock state, and I'm going to discuss more about coherent states in the next class.
Let me stop here for today. In this lecture, we have discussed and studied about the so-called second order correlation function, and we have calculated the second order correlation function for various quantum states of light, and we discussed briefly about the coherent states of light. We'll continue our discussion about coherent states of light in the next lecture, and apart from coherent states of light, we are going to discuss another quantum states of light, which is the squeeze states of light. So see you in the next lecture. Thank you so much.